Good day. Let's have ourselves another chemistry live session for today. Again, the core focus for this live class would be on O-level examinations, not just limited to just Jamb, but as well Waec as well. So we are taking the entire scope. We're picking shortcuts where necessary, as the case might be. So let's go on with our live class for today. Now, in this live class, our focus will delve on one basic thing that holds the entirety of what chemistry stands for together, and that's the concept of matter. Now, on a blank note, of course, we would always define that matter is, in fact, anything that has mass and occupies space. So these are like two key concepts we put into our definitions. The fact that it has mass and it occupies space. But then we can always extend this concept beyond this. We can talk about the fact that matter, in fact, consists or exists in three major states. There are three major states in which matter exists. We talk about the solid state, the liquid, and of course, the gaseous state. These three states exist in every single scenario, whether it's at rest or otherwise. This is the three acceptable states to which we have matter exist. In fact, you'll find out that as far as the periodic table is concerned, the periodic table being the generally accepted arrangement of every single noted element within chemistry, you'll find out that all the elements within the periodic table are also classified or categorized with respect to them being solids, liquids, or gases. Of course, in your periodic table, you'd find out that you have your groups. Of course, these groups are in your vertical columns. You have your groups, you have your group 1, 2, 3, and all of these ones here are termed as solids. And then you have, of course, you have your transition elements in the middle here. And then you have on this side, you have your other groups of elements. In this place, you have your group 4, which is weather kind of elements. They are around the middle. They are not much on this side. They are not much on this side. But more importantly, on this side, we would have, and this is the group we want to pay more attention to. We have the solids here, fully solids here. Then we have your group 5, 4. You have your group 5, 6, 7. And around this edge, you have more of them being liquids. And then you have your last group, which is termed the group 8 element, or called the group 0 elements. And these ones are predominantly gases. So you find out that in your periodic table as well, the categories or the categorization of elements within the periodic table still follows that same major states of matter: solids, liquids, and gases. Of course, some of these groups have general names we call them. For instance, we will call the group 0 elements as the inert gases or as noble gases, which is the state in which every other kind of element strives to ensure they become. That's the state of nobility or stability. We have elements like the group 7, which are halogens, and so on and so forth. But then, more importantly, which is the focus of what we want to drive out, is the fact that the solids are categorized, the liquids are categorized, and then the gases are also categorized. But then this is not the only thing. This is not the only thing we want to bring out as far as this concept of matter is concerned. As we have seen, whether being solids or liquids or gases, one general concept that brings all of them together is the fact that they all exist as elements first and foremost. They all exist as elements. Now, as elements, how exactly can we further try to clarify or define what it means to be an element? We can carry out basic definitions on the term element by using, in fact, the concept of atoms, the molecules, and the ions for those elements. Of course, when we talk about the atom, as far as first basic definitions of chemistry is concerned, Dalton went ahead to define atom as the smallest indivisible part of an element, although modern chemistry has found and has correctly found that we can in fact break down atoms into smaller parts. What about molecules? We are talking about collections or groups of atoms that can still exist as an entity. And then when we are talking about ions, what do we mean? We are talking about charged atoms. That is, atoms that have gone into reactions. All these different categories have their significance. Now, why exactly is that significance important? Let's see that in a minute. Now, of course, recall that when we were talking briefly about the periodic table, we talked about the existence of the group 8 elements or the inert gases. They are called noble gases because of the state in which they find themselves, which is the state of stability. They have absolutely no reason or no need to go into any kind of reaction. They are stable. Why do we know this? Because in their outermost shell, and now this is the most important property that can easily be found about noble gases. In their outermost shell, they either have 2 valence electrons for some of them, or they have 8 valence electrons at all times. And this is true for all the noble gases. In fact, the one that has 2 valence electrons is the one that exists at the very top of the periodic table, and that is helium. But the rest of them, they have 8 valence electrons. And of course, we'll be talking about neon. We'll be talking about neon and so on and so forth. All of these have 8 valence electrons as we proceed down the periodic table. Do not forget that when we talk about the periodic table, it is general to talk or emphasize on the first 20 elements, which would quickly list in terms of their atomic symbols. We have hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So this is the first 20 elements in terms of the atomic symbol. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon, potassium, and calcium. We have all of this. So helium, which is the first member of the noble gas, has 2 valence electrons. Neon, which is the next member, has 8 valence electrons. And of course, even if you look at argon, which is still the next member, it also has 8 valence electrons. Elements that have 8 valence electrons in their outermost shell are said to be stable. What does that mean? It means that they have absolutely no reason to want to go into reaction, to want to go into a chemical reaction where they are needing to either accept or give out electrons. They are stable in the outermost shell. That's why we call them noble gases. Literally, it means that they have absolutely no reason to do whatever the common folk is doing. Basically, that's what it means, right? So in terms of chemistry and what we do when we carry out chemical equations or reactions, we are always seeking to take other kinds of elements towards that level of stability. That is, towards having 8 valence electrons or sometimes 2 valence electrons. The phenomenon or the process of achieving 8 valence electrons is what we term as the octet structure. While having 2 valence electrons is what is termed as the duplex structure. These are key terms. So when you hear duplex structure, it means they are saying that yes, it has achieved 2 valence electrons in the outermost shell. And if you hear the octet structure, we are saying it has achieved 8 valence electrons in the outermost shell. This is basically the reason why elements go into reactions. Of course, we can still go beyond this. We can still talk about something even much more interesting, more than this, right? We have talked about the fact that even though Dalton went forward to determine that the atom is the smallest indivisible part of the element, further researches into chemistry showed us that yes, we could break down that element. Now, when we break down that element, what exactly would we find inside? Within the nucleus or within the constituents of an atom, so within the constituents of an atom, we have started, of course, with matter. So we can obviously term this as matter. So we have given the random description of what matter is. And then for matter, we have explained the states of matter that we have, which is solid, liquid, and gas. We have also talked about the fact that this solid, liquid, and gas exist as elements that can be classified in the periodic table. And those elements can either have constituents that are atoms, which is obviously what elements are formed with, or can also exist as molecules, or can exist as ions when the atoms are charged. And then we talked about the outermost shell, which is the basis for carrying out chemical reactions, where achieving 2 valence electrons, which is the duplex structure, would make you stable in some cases, or achieving 8 valence electrons, which would give you the octet structure, will also allow you to be stable in some cases. Now let's talk about the constituents of atoms that are now going into those reactions. Of course, we have said, okay, the element is going into reaction to achieve stability. Now, when it goes into reaction, what exactly is going into that reaction? What part of that element is going into the reaction? The part of the element that is going into the reaction is the atom. However, it is not even the atom completely that is going into the reaction. Notice here we have used the term valence. However, we have also used the term electrons. Where exactly do we get these terms? That is exactly what we are trying to figure out now. Now let's look at the constituent of the atom. In the atom, we can find 3 major constituents. We will talk about the proton, we will talk about the neutron, and we will talk about the electron. Very interesting. In fact, in the nucleus of the atom, we will find, so let's make a quick sketch of the nucleus of the atom. Within this nucleus, we will find the proton and we will find the neutron. And then orbiting around the nucleus of the atom, that is just like saying orbiting on the circumference of the atom, we will find the electron. Now, what are the properties these 3 constituents of this atom share? What makes them so unique? Let's look at it. For the electron is the part of the atom that carries the negative charge. So it is negatively charged. And in fact, the mass of the electron is in fact referred to as 1/1840 units when compared. Of course, it is because of this small mass, that is why it can in fact rotate or orbit around the circumference. It is because of this small mass that it has, that is why we can in fact see it orbiting around the nucleus. These ones are now exist within the nucleus. What would now be their mass? First, let's talk about the charge it carries. The proton is the one that carries the positive charge. And its mass is exactly 1 unit. While the neutron has no charge, it is neutral, but its mass is also 1 unit when compared to the atom. This is why the proton and neutron exist within the nucleus, while the electron with a small mass orbits around the nucleus. This is the states of the constituents of the atom. It now goes further. Because of the fact that the electron is the one orbiting around the nucleus of the atom, it obviously follows that it will be that electron that will be closest to the reaction phase for that element. Because it is the one orbiting around the nucleus of the atom, it is the one that will be most exposed to reactions. Before you can get to the proton and neutron within the cell or within the atom, you would first and foremost have to go through the electrons. And that is why the electrons are said to be the most important and essential constituent of the atom as far as charges and carrying out reactions are concerned. And that's why when we define outermost shells and the valencies and the octet structure and the duplex structure, we are defining it with respect to the electrons because they are the ones orbiting around the nucleus of the atom. Very, very important fact. Now, the next question that would now pose a very big effect on our concepts will now be, all right, we have said the electron is the one that carries out the most effect on the reactions. How exactly do we know how those reactions will take place? How exactly do we know what is necessary for those reactions to take place? Very simple. The number of electrons that will take part within reactions will be determined with respect to the atomic number of that element. The number of electrons that are set forward in a reaction is determined by the atomic number of that element. Now the question is, how do we know the atomic number of that element? The atomic number of an element is defined as the number of protons in an atom of the element. The number of protons in an atom of the element. We can also define the atomic number, and this is very important and exciting. We can also define the atomic number as the number of electrons in an atom of a stable element. Very important. So we can either define the atomic number as the number of protons in an atom of an element or the number of electrons in an atom of a stable element. Now the question is, why exactly did this have to go in for the case of the electron? Very important, because the electron again is orbiting around the nucleus of the atom, which means that it is always exposed to reactions. What that means is that if the element is not stable, it will be entering into reactions. And if it enters into reactions, it means that there is always a possibility that the electrons can either have been transferred out of the element or it has accepted more electrons into the element. If that is the case, then the number of electrons will not be able to correctly satisfy the atomic number because the atomic number is supposed to be unchanged. However, you notice that if you define it as the number of protons, then there is absolutely no problem because the proton is always within the nucleus. So it is never going to be exposed to any reaction that will cause it to leave the atom. As such, the atomic number will remain unchanged. However, if the element is stable and is not going into reactions, then the electrons too will not leave the atom, even though it is orbiting around it. And as such, at that level, the atomic number will hold. Now, this particular definition is in fact much more important than this. How? Because it is because of the fact that the electrons is the one exposed. We can now use that concept of electrons to determine how much or by how much the number of electrons within an element would either increase or decrease. We will get to that within a few moments. But first, let us define something else. Let us define the mass number. Now, how do we define the mass number? The mass number is defined, again, as the sum of the numbers of protons and neutrons in an atom of the element. Which means if you put the number of protons and the number of neutrons together, then that would give you the mass number. Another way to define it is to say it is the sum of the number of electrons and neutrons in the atom of a stable element. That will work as well. So this defines the mass number, this defines the atomic number. Now, before we delve into what the mass number brings to the table, let us talk about what the atomic number brings to the table. In terms of the atomic number and in terms of the effect it has on the reactions of that element, let's quickly consider how we can determine or how we can arrange the electrons within an element in their various configurations. The atomic number has been defined as the number of protons in an atom of an element or the number of electrons in an atom of a stable element. That atomic number, of course, if we were to pick this second definition, which is the number of electrons, recall that the electrons are always orbiting around the nucleus of the atom, which means that they are always in orbit. Those orbits can be referred to as shells of the element. Of course, because they are in shells of an element, it means that it is obviously going to be strenuous for all of them to fit into just one shell. So how then do we arrange or configure them within that orbit that they find themselves? This is what we term as the orbital configuration. So when we say orbital configuration of an element, we are simply talking about the arrangement of the electrons of that element into orbits or shells. Simple. The arrangement of elements the arrangement of electrons of that element into orbits or shells. Now, how do we make that arrangement? We make that arrangement by following a simple process, at least for the first 20 elements. We follow a simple process. What is that simple process? Number one, the first shell cannot take more than 2 valence electrons. Of course, do not forget that when we talk about valency, we are talking about the combining power of an element. The valency determines the combining power of an element, while the oxidation number talks about the charge that element appears to have. Now, for orbital configurations, we have that the first shell of that element cannot take more than 2 valence electrons. The next shell would only be able to take up to the octet structure. Then the next shell takes up to another octet structure, and so on and so forth. We will carry out or we will see the process of arranging for the first 20 elements. Now, let's make a quick caricature. This is our first shell. It cannot take more than 2. The next shell will take another 8 elements, 8 electrons. The next will take another 8 electrons till we have exhausted the atomic number of that element. That is how the orbital configuration is carried out. Now, let's put this into perspective. For the first element, hydrogen, with atomic number 1, of course, atomic numbers are written on the left corner of the element, left, while the mass number comes on top, on the right, on the left side as well, left top or top left, then this is bottom left. So here, the orbital configuration here is just 1 because there's just 1 electron, and then if you were to draw the shell, you just have 1 electron here. For the next one, which is helium, which is 2, that is of course a noble gas, you have it as 2, and you have a shell complete, 2 electrons. Now, electrons in the orbital or in the orbits are written in pairs. Electrons in the orbits are written in pairs. Very, very important. So do not be tempted to do something like this and say, yes, you have still denoted 2 electrons. No, they have to be in pairs. So if you have 2 electrons, you complete a pair. If you have 3, you complete 1 pair and leave 1 separately, like in the case of lithium. Here we have 3 electrons. How do we classify it? The first shell is complete, 2. Then we move to the next shell. 1, 2, 1. This is the orbital configuration for lithium. How do we write that? 2. And then the next shell, 1.